Conduit depth requirements vary based on the application, distinguishing between residential and commercial settings. For residential applications, the minimum burial depth for conduit is 18 inches, which is equivalent to 457 mm below grade. In commercial settings, a greater depth is required, mandating a minimum burial depth of 24 inches, or 610 mm below grade. The selection of conduit type also depends on whether the installation is residential or commercial. In residential scenarios, non-metallic or plastic conduit is permitted, provided it has a minimum trade size of 1/2 inch, corresponding to 13 mm. For commercial installations, either metal or non-metallic conduit can be used. However, the minimum trade size increases to 3/4 inch, equivalent to 19 mm. Grounding is of paramount importance, especially when dealing with ground fault interrupters, or GFIs. A GFI must be connected to a properly grounded electrical system to function correctly. The grounding conductor must be connected to the grounding terminal on the GFI and subsequently to the ground bar within the electrical panel. When utilizing metal conduit, the conduit itself can serve as the grounding conductor, given its conductive properties. Conversely, when employing plastic conduit, a separate grounding conductor must be run internally alongside the circuit conductors because plastic is a non-conductive material. When installing electrical systems underground, several key factors must be considered to ensure safety and compliance with electrical codes. These considerations range from the type of conduit used to the depth at which it is buried, as well as the proper grounding techniques. Conduit depth is crucial because it protects the electrical wiring from physical damage due to digging, soil movement, or other activities on the surface. The National Electrical Code, or NEC, specifies minimum burial depths for different types of conduit and applications. Firstly, for residential applications, the NEC typically requires a minimum burial depth of 18 inches for direct buried non-metallic conduit. This depth helps prevent accidental damage from common residential activities like gardening or installing shallow landscaping. Secondly, for commercial applications, where there is often heavier traffic or potential for digging, the required burial depth is greater, typically 24 inches or more. This increased depth provides a higher level of protection against damage. Thirdly, the type of conduit also affects the required burial depth. Rigid metal conduit, or RMC, which is more resistant to physical damage, may be permitted at shallower depths in some cases compared to non-metallic conduit. Non-metallic conduit, such as PVC, is lightweight and corrosion resistant but requires greater burial depth to protect it from damage. There are several types of conduit available for electrical installations, each with its own advantages and disadvantages. Firstly, rigid metal conduit, or RMC, is a heavy-duty conduit made of galvanized steel or aluminum. It provides excellent protection against physical damage and can also serve as an equipment grounding conductor. Secondly, intermediate metal conduit, or INC, is a thinner-walled version of RMC that is lighter and easier to work with. It offers similar protection to RMC but at a lower cost. Thirdly, electrical metallic tubing, or IM, is a lightweight, thin-walled conduit made of steel or aluminum. It is commonly used for indoor wiring in residential and commercial buildings. Fourthly, flexible metal conduit, or FMC, is a flexible conduit made of steel or aluminum. It is used in locations where flexibility is needed, such as connecting to motors or other equipment that may vibrate. Fifthly, liquid-type flexible metal conduit, or LFMC, is a flexible conduit that is coated with a waterproof plastic covering. It is used in wet or damp locations to protect wiring from moisture. Sixthly, non-metallic conduit, such as PVC, is a lightweight, corrosion-resistant conduit made of plastic. It is commonly used for underground wiring and in locations where corrosion is a concern. Grounding is essential for electrical safety. It provides a path for fault current to flow back to the source, tripping a circuit breaker or fuse and preventing electrical shock. Ground fault interrupters, or GFIs, are devices that protect against electrical shock by monitoring the current flowing in a circuit. If a ground fault is detected, the GFI quickly interrupts the circuit, preventing injury. Firstly, all GFI must be connected to a properly grounded electrical system. This means that the grounding conductor from the GFI must be connected to the grounding terminal on the GFI and to the ground bar in the electrical panel. Secondly, for metal conduit systems, the conduit itself can serve as the equipment grounding conductor. The conduit must be properly connected to the electrical boxes and equipment to ensure a continuous ground path. Thirdly, for non-metallic conduit systems, a separate grounding conductor must be run inside the conduit along with the circuit conductors. The grounding conductor must be connected to the grounding terminal on the GFI and to the ground bar in the electrical panel. Several best practices should be followed when installing electrical systems underground. Firstly, always consult the NEC and local electrical codes to ensure compliance. These codes provide detailed requirements for conduit depth, conduit type, grounding, and other aspects of electrical installations. Secondly, use the appropriate type of conduit for the application. Consider the environmental conditions, potential for physical damage, and cost when selecting conduit. Thirdly, properly install and support the conduit. Follow manufacturer's instructions for cutting, bending, and joining conduit. Support the conduit at appropriate intervals to prevent sagging or damage. Fourthly, ensure proper grounding. Verify that all electrical boxes, equipment, and conduit are properly grounded. Use appropriate grounding connectors and techniques. Fifthly, protect wiring from damage. Use bushings or fittings to protect wiring from sharp edges of conduit. Avoid pulling wiring too tightly, which can damage the insulation. Sixthly, label and identify circuits. Clearly label all circuits in the electrical panel to indicate their purpose and the areas they serve. This helps with troubleshooting and maintenance. Seventhly, inspect and test the installation. After completing the installation, thoroughly inspect it to ensure that all connections are tight and that the wiring is properly installed. Test the circuits to verify that they are working properly and that the GFI are functioning correctly. Regarding specific NEC tables and articles, several are relevant to underground conduit installations. Firstly, NEC Table 300.5 provides minimum cover requirements for underground wiring. This table specifies the minimum depth at which different types of conduit and wiring must be buried based on the voltage and application. Secondly, NEC Article 310.15 addresses ampacity of conductors. This article provides guidelines for determining the maximum current that a conductor can carry safely based on its size, insulation type, and installation conditions. Thirdly, NEC Article 250 covers grounding and bonding. This article provides detailed requirements for grounding electrical systems to ensure safety. Fourthly, NEC Article 352 covers rigid polyvinyl chloride conduit, or PVC. This article specifies the requirements for using PVC conduit, including its installation, support, and grounding. Fifthly, NEC Article 344 covers rigid metal conduit, or RMC. This article specifies the requirements for using RMC, including its installation, support, and grounding. When installing underground conduit, it is also essential to consider the potential for corrosion. Underground environments can be corrosive due to moisture, chemicals, and soil conditions. To prevent corrosion, use conduit and fittings that are specifically designed for underground use. For example, galvanized steel conduit is often used because it is resistant to corrosion. You can also use non-metallic conduit, such as PVC, which is inherently corrosion resistant. In addition, it is important to properly seal the conduit to prevent moisture from entering. Use waterproof connectors and sealant to seal all joints and connections. You should also consider using a corrosion-resistant coating on the conduit. This can provide an extra layer of protection against corrosion. Before backfilling the trench, inspect the conduit for any damage. If you find any damage, repair it immediately. Use appropriate repair methods, such as patching or replacing the damaged section of conduit. When backfilling the trench, use clean fill material that is free of rocks and debris. This will help to protect the conduit from damage. Compact the fill material to provide a stable base for the conduit. After backfilling the trench, mark the location of the conduit. This will help to prevent accidental damage in the future. You can use markers or signs to indicate the location of the conduit. In addition to the above considerations, it is also important to follow any local regulations or requirements. Some local jurisdictions may have additional requirements for underground conduit installations. Be sure to check with your local building department to determine if there are any specific requirements in your area. When working with electricity, safety should always be your top priority. Always to energize the circuit before working on it. Use appropriate personal protective equipment, such as gloves and eye protection. If you are not comfortable working with electricity, hire a qualified electrician. The information provided here is intended for general guidance only and should not be considered a substitute for professional advice. Always consult with a qualified electrician or electrical engineer before undertaking any electrical work. In summary, proper conduit depth, conduit type, and grounding are crucial for safe and compliant underground electrical installations. Always follow the NEC and local electrical codes, use appropriate materials and techniques, and prioritize safety.